Okay. So we've looked at the basic square function. We have looked at the square root. We did cube root, and then of course we did parabola opening on the right, semicircles. So getting into piecewise functions, basically it means that, obviously your function is defined over pieces, which means we actually break our domain down into pieces, and for each piece you have a different definition, a different function. So we're saying different formulas are used in different regions of the domain. You can have two or more pieces depending on the function itself, so that's why they're called piecewise functions. Now, we would normally not think about the absolute value function as being a piecewise function. If you actually think about, does anybody know what kind of shape an absolute value function has?
V.
Yeah, it's a V. So you can kind of think like a parabola, but instead of being curved lines, it's a V, right, with straight lines. So you really don't think of a absolute value function being piecewise, but this is actually how an absolute value function is defined. So we are saying on the part of the domain where your x values go from 0 to infinity, so 0 and anything greater than 0, we actually define our function as x. And then on the negative side of our domain, on the negative x values, we're actually defining it as negative x. So let's take a look at what that actually does. So instead of defining it by using that absolute value symbol, we're defining it as a piecewise function, where the first part where it's x, second one is negative x. This is defined for x values greater than or equal to 0. These ones are for less than 0. So if we were creating a table, if I was only going to use 0 and positive values, so anything, right? And I can keep going. For these positive values, this is defined on this little portion here, which means I can only use the y equals x as part of my definition. Now, if I start using x on the negative side, so that means I'm going from -1, -2, -3. For these values, actually, so when I'm using x values that are negative numbers, I'm actually going to use the second piece, which is telling me y equals -x. So when it says y equals x, whatever is your x value, that becomes your y value, right? X equals y or y equals x, which means these guys will stay as it is. But for the negative side, where I'm using negative x values, they're asking me to use y equals -x, which means there's the negative coming from the function definition itself, and there's the negative coming from the x value itself. So those two negatives will give us what? Positive. So you can see why, when we define our absolute value function in pieces, why those values always end up becoming positive, right? Positive values stay positive, negative values become positive, and we know that's true for absolute value, but that's if we define our function in this way. So that's honestly the original definition, or whatever you want to think about it as, for absolute values. So anything from 0 and greater than 0 will stay the same. Anything on the negative side will become a negative of itself, which basically ends up making it positive.
And I mean, it's just because it's absolute 0, so it's just the distance away from 0, right? I mean, it just goes back to that same.
Yeah, so it's just you're breaking your domain down. So if you think about this in terms of a graph, these would be x equals 0 right here, right? And then x will be positive going this way. And then x would be negative going this way, right? So we are basically saying for all 0 and positive values, use the first part of your definition. For all the negative x values, use the second part of your definition. So we can actually use these same points once we start looking into the graph of our absolute value function here. So we've got 0, 1 and 2, and let's use -1, -2 here if you want to put these in a little bit more of an order. We can do -2, -1, 0, 1, and 2. Okay, so remember, negatives will become positives, 0 will of course stay 0, and positives will stay positives. So let me actually do a little bit of a better graph for this guy. This is what, 7? You have 0, 0, 1, 1, 2, 2, -1 becomes +1, -2 becomes +2. So is it a function? Yeah, it is, because it is going to pass the vertical line test. So it is a function. What can you say about the domain and range for the absolute value function? Yes, Rexy?
Domain is -infinity to infinity.
Very good.
Because it can be, it can slide back.
Going either direction, and I'll come back to the graph and talk about it in a minute. Range?
0 to infinity, including 0.
Very nice. Alrighty. So 0 to infinity, including 0. Oh, not you. Okay. So this arm of our graph, of course, as it's going up is also going left. So that's why it's going to -infinity for the domain. And same thing here, as this arm goes up, it's also going to the right, which means he's going towards +infinity on the x. So your domain in this case is going to be negative to +infinity, as we looked at. And then again, you should notice there is no part of our graph on the bottom side, right? On the negative side of the y-axis. Your graph is starting at 0, and those arms, of course, are going to go up, which means you're going towards +infinity. And since we do have a graph at 0, you are going to include that 0. So like they were saying, this is the simplest absolute value function that you can think of. But obviously, let's look at some different examples here. Is everybody okay on that graph? Yeah, okay, so let's look at what happens here. Okay. So you'll notice for the first graph, we are defining from -2 to +2, including our endpoints, right? So our x values for this portion is going to be between -2 and +2, and you would say it's less than and equal to, which means we're including the endpoints. Once we get two numbers greater than 2, we switch the formula, and now we are using 4 minus x for our domain where x values are greater than 2. So let's see how we can go about working with this guy. So f of x, was that square root of x plus 2?
Yeah.
And this is, of course, defined from -2 to +2, and then the other one was 4 minus x, defined for x values greater than 2. So when you're setting up your table for this, obviously you want to use anything from -2 to +2 for that first part. So let's say we're doing this for the first part of our piecewise function. So I can start from -2, -1, 0, 1, and 2, and of course anything in between those. Now you'll notice we cannot go any lower than -2 anyways, right? Because otherwise we start getting into the imaginary number territory and we're not dealing with those. Once I hit 2, that's how far I can go for that first part. Now for my second part, where we are saying y equals 4 minus x, I can use any numbers greater than 2, which means technically I can use 2.000000001, right? Because that is a number greater than 2. So we honestly want to know what happens at 2. So even though we are not including 2 on the second piece, we are actually still going to start at the number 2, because like I said, you can be literally 1/10,000 or 1/1,000,000th of a point away from 2, but we still want to know what it's going to do. So that's why we always include that number, even though they're not asking us to. And then you go anything greater than that. So we can do 3, 4, I don't know, 5. I think that should give us enough idea on those pieces. So let's start with our first piece, square root of x plus 2. When I put in -2 for my x here, what do I get? 0. Yeah, you're going to get 0 because you're doing -2 plus 2, which is square root of 0, and we know square root of 0 is 0. What will we get with -1? 1. Yeah, square root of 1 is 1. With 0? 2. Okay, great. No.
2.
2, right? 0 plus 2 is 2. What is square root of 2? It's not a happy number for sure. Approximately? 1.414, and it keeps going. Okay. With +1, what do we get?
3.
And you guys love 1. 3, right? What is square root of 3?
1.7.
Yeah, 1.7. And the last one. It will be 2. You are going to get square root of 4, which will, of course, simplify into 2. So we've got 3 good numbers in there, and 2 are approximate numbers. I mean, we could probably kind of use them as guides, but those 3 numbers should really help us out. Now, what do we get here? 4 minus 2 is what?
2.
4 minus 3?
1.
4 minus 4?
0.
All right, 5 minus 4. 4 minus 5?
-1.
There we go. -1. Okay. So go ahead, draw your graph, see what it looks like till I catch up with you. So we're going on to 5. Sorry. So let's see, we're starting out at -2, 0. -1, 1. And then 2 and 2. And you've got approximations with 1.4 and about 1.7. I'm a little off on that. Let's see. Now this is actually what I was really hoping that we would end up with. I have the same ordered pair, 2 and 2 from my first piece, and 2 and 2 from my second piece. So this is crucial because that's telling me the 2 pieces of our function are actually joined together at this point, 2 and 2. Because if those numbers came out to be different, that would tell us there's a little gap, right? But since they came out to be the same number, that means the 2 pieces of our function are connected. So we're going from 2 and 2 to 3 and 1, 4 and 0, and then 5 and -1. So this should actually be a straight line that goes down like this. Okay, just to show you what this graph should look like, let's go to, so we have square root of x plus 2, and we've got 4 minus x. So the idea is we should go from -2 to 2, just this portion of our graph is what we're seeing from the square root of x plus 2, right? And then it stops right here because we don't have this portion going to the right. And then with our straight line right here, we're starting to go down this way. So if you ignore those upper halves, we should have this little curve, and then our line going down is what our function should look like. So you've got part of that square root function, right? So that's part of a parabola that we're seeing on that first part from -2 to 2. And then we're seeing a line with a negative slope on the right-hand side here. Everybody got the graph? Okay. Now, let's see. What are they asking us? Domain and range? So what will the domain and range for this function be? Yes, Amy?
The domain is -2, 5. -2 and 5. No? Oh, sorry, to infinity. Sorry.
Yeah, is that what you're going to say? Yes, because 5 would mean our graph stops right here then, right? Like it did with the circles. But this line actually will keep going, so that tells me we're starting at -2, and then as this line goes down, it's actually going to keep going to the right. So that's why you are going from -2 to infinity. Now what do we put on -2? Yeah, including. Because we obviously have a point at -2. Okay, very good. Now take a second and think about it. What should your range for this function be? Really?
-infinity to 2.
Yeah, because we're not going to keep going up, right? Our graph stops at this point because there's nothing to make our graph go up. So yes, this arm is definitely going down. So he's going towards -infinity, but it comes up and it stops at 2. So you are going from -infinity to 2, and of course we're still including 2 because we do have a point at 2. Does that make sense? No?
My only question is, I don't know how you know where and like when to stop. Like I guess that makes sense, like where you include and stop when you look back at the equation. But I guess when you showed us like the other graph, like it kept going. So in my mind, it looks like it should keep going from infinity to 1.
Yeah, and that would happen if, honestly, if we didn't have this little square root function and this was just a 4 minus x function. In that case, it would have kept going. But the idea is my 4 minus x only started at numbers greater than 2, right? So we're not using anything less than 2, which means my graph for the 4 minus x basically starts here. There's no graph going this way, so I don't have a function that keeps going on the left-hand side.
Only because it told us up there? That's what you're saying.
Yeah, because they told us that only x values greater than 2 is what we start here. You had your hand up?
Oh, when you basically explained it, because it wasn't really a question. I mean, I thought the same thing at first, like on the website graphic showed it going up, but that's because you didn't include x.
Yeah, because there may be a way, but I actually don't know how to restrict my domain on that calculator. So because I was just showing you what the proper shape should look like since my graph looks so funny. That was the idea of showing you that.
Which is like the straight line.
Yeah.
The intersection point is where you stop.
Right, right, because our graph is not going to continue to grow in the left-hand side. Anybody else have question on that part of why our domain and range are what they are? Okay. And again, you know, if something pops up on your homework you need help with, let me know. So that was number 8. Okay. You know what? Let me see what you guys can do with number 9. So follow what we did with number 8, and it's going to be about in the same process. Okay, so let's take a look at this one here.
Here, ¿quieres que me
Say
eche
this is x squared.
Así soy. Then I have it right.
So just a couple of you did not include that -1 in there. So yeah, I know it's saying less than -1, but remember it can literally start from like the 1/1,000,000th of a point right next to -1. So even though they're not including -1 in that function definition, we still want to use -1 for this guy here. So of course, since we're taking squares on all of these numbers, they're going to become +1, +4, +9, +16. For our second piece, which is the -x, they're asking us to go with points starting from -1 and greater than that. So we can do -1, 0, 1, 2, 3, and again, as far as you want to go. Now, since this is basically taking the negative of x, your signs will change. So this becomes +1, I guess 0, -1, -2, -3. And again, like I said, if we know the two pieces of our graph are going to be connecting, then these points should come out to be the same. And of course, they do, right? Which means, again, there's no gap in our function. So if we graph this again, most of you had your graphs done, especially the last couple of rows. We're going -1, -2, -3. I actually need to go up to 9 on this though. So -1, -2 is at 4, -3 is at 9, and then we go down to 0, 0. So this part, since it's coming from the x square, should actually look part of a parabola, right? Because of that x square, and again, it should stop at -1, and then at -1, we are changing our function. So this is again a line, straight line with the negative slope. So this is what our function looks like, and again, just to show you graphically what this would look like. This should be x squared, and this should be just -4. This is where the change is happening. Again, we are ignoring this part of our graph, and then once we hit -1, we are ignoring this part of our parabola. So you're literally just seeing this little portion here. At -1, it changes and goes down into this graph. So you end up with a graph that looks like this. This portion right here is our parabola, and then at -1, it changes and becomes a straight line going down. So domain and range. Okay. For domain, okay. So yeah, this arm of our graph obviously will start going towards the left, right? Because as it goes up, it makes its way to the left. This arm, obviously, we can see as it's going down, it's also heading to the right. So you're looking at all real numbers, negative to positive infinity for your domain. And what can you say about the range? It is the same thing, yeah. Because obviously, he's going up, he's going down. They're going to cover the entire x and y values. So for both domain and range, you're looking from negative to positive infinity. Any questions on that one? So we're talking about piecewise functions can also be used in an application such as shipping charges, because in that case, based on the weight of your package, of course, the price will keep changing. So in this case, your interval is literally going to go from like 0 to 1 pound, or are we doing this in pounds? Yeah, we're doing it in pounds. And then you can go from 1 pound to 2 pounds, 2 pounds to 3 pounds. So depending on which part of the domain your package falls into, it's going to have a different price range. So you will notice here, we're not including 0, but we're including 1, right? Because you can't really have a package which is 0 pounds, which means you're shipping air. So you start at 0 point something, right? Maybe half a pound, maybe a quarter pound, depending on what you have in your package. So you're starting at 0, not including it, but right up to 1 pound. So as long as your package weighs right at 1.00 pounds, you're going to be paying that first tier. But the moment it goes into 1 point something, you're now going over to the next interval, right? And that's going to be up to 2 pounds. So we're saying, let's say for 0 to 1 pound, you're only going to pay $3. But the moment you go up from 1 to 2 pounds, now that shipping and handling charge has gone up to $4. And then maybe from 2 to 3 pounds, maybe it goes up to $5. Obviously, these prices are not the real deal, right? We're just kind of setting up an example here. So in that same sense, we can actually think about our greatest integer function. This is actually also a piecewise function. And in this case, you will notice we are using this symbol, which I don't know if you can see that on your paper or not, but it should be 2 little brackets that we are using to define that x. So it's not a single bracket like we use here. It should be like 2 overlapping brackets. So that's your greatest integer function, or sometimes we just call it the integer of x, or the int of x. Now this definition we're saying is defined to be the largest integer that is less than or equal to x. So think about it, the greatest integer function, that little symbol, the definition is the largest integer that is less than or equal to x. So if I have a number like 5.01, we're thinking less than or equal to x, the largest integer. So for 5.01, the closest one it's going to be at is 5, right? Because that's my largest integer, which is less than 5.01. If you're looking at 3.2, again, what is the largest integer that is closest to 3.2, but it's less than? Which will again be 3. The only time it's going to be equal to is if you have just a whole number or an integer in there and not anything with a decimal. But if you look at it, anything that has a decimal, you are thinking less than. So let me give you a couple more numbers to work with. So for our greatest integer function. And this is defined as x, okay? So if we give you 2.51. What would our greatest integer be, which is less than or equal to the number that you have in the symbol? If it helps, visualize a number line. So I've got 2.51, which is going to be between 2 and 3, somewhere over there. I think I heard somebody say, yeah, 2. Because you're talking about what number is less than or equal to. So obviously this will not be equal to, because we're talking in terms of integers, which means 2 is the nearest integer, which is less than this value. So this guy equals 2. Think about the same thing with 7.95. Again, this is not a rounding problem, guys. 7.95 will be between 7 and 8. And let's say it's going to be somewhere over here. The largest integer that is less than or equal to this value. 7, yeah. So again, you're not thinking rounding. You're not thinking which number is it closer to. We don't care. It's got to be the integer, which is the largest one, but still less than. Okay, negative 4.86. Negative 5. What do we got? What do we think, folks? Because we're looking at negative 4.86, which will be, I don't know, somewhere over here. So yeah, we're thinking less than, right? So on the negative side, then we got to start thinking in the opposite direction. So yeah, very good. It is going to be negative 5. Is everybody okay with how we define greatest integer function? Any questions? Okay, good. All right, let's get back to our example here. Then we're talking about just the basic graphing of your greatest integer function. And I was not able to replicate what your textbook has. You can see Word does not let me use those little brackets, but that's the same function we're talking about here. So the way we define our domain in this case, let's take this. What number was that?
That was 10.
10, thank you. So the way we actually define our domain for this guy, it's kind of like that shipping example. Yeah. It's actually kind of going to be interesting how we do our little table here. So I'm going to start from 0 and head to the right, and then I'll come back to the negatives. So you are actually going to define this as the interval going from 0 to 1, but we actually include the lower limit and not the upper limit. So it's a little bit different from the shipping example we just looked at in that paragraph. So think of all the numbers that fall between 0 and 1. And as a representative, think of the number 0.5 because that's right in the middle of this interval. So using our greatest integer function, what will 0.5 be equal to? 0, right? Because again, you're going smaller, less than. So that means all the numbers that fall from 0 to 0.99999, right? Because we're not including 1. All of those numbers are going to fall back to 0. So anything that's going to be in that interval. So now we go from 0 to 1 to 1 to 2. And again, as a representative for this little interval, this is 1.5. So what would that integer be? 1, yeah. All right, so go ahead, get you a couple more intervals in there. And you know, this can keep going, but we're not really going to write all of them down. So go ahead and tell me what these numbers should be. Jamesy?
I'm just in why we, oh, between 0 and, okay, never mind.
Yeah.
Between 1 and 2, between 2 and 3.
So what will my y values be here? You want to say?
2, 3, 4.
Yeah. So you can kind of see a trend at this point, or hopefully you can. It ends up becoming that lower limit number, doesn't it? The one we're including. Okay, now think on the negative side, because these were all positives. Now let's go, we went from 0, which means I need to start from -1 to 0. -2 to -1, -3 to -2, and so on and so forth. So now we're on the negative side, what will my y values be? No. Yeah, go with the lower limit, right? -1, -2, -3, and it keeps going. Alrighty, let's see. So we're going from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Okay, so now we really got to think about how this graph is going to work. Because our domain is broken up into literally 1 unit, right? So we're saying all the numbers between 0 and 1 are going to be at 0, which means all the numbers between 0 and 1 are going to be at 0. We are including the left-hand side, not including the right-hand side, which means I will have a closed circle right at 0, because that's the number I'm including, but I'm not including 1, which means I am going to have, that did work out, an open circle at 1, right? And since all of these values are going to be 0, that's why I'm drawing a straight line from 0 to 1. Again, a closed circle at 0, an open circle at 1. Then we're going from 1 to 2, right? We're changing our domain now. We're going from 1 to 2, same thing, closed at 1, open at 0, but now my y values are going to be in line with 1, which means my y values are going to be in line with this guy. I'm going from 1 to 2, closed circle at 1, open circle at 2. Excuse me. So what do you think our next graph, next part of the graph should look like? Yeah, you're basically climbing stairs, right? It kind of looks like a stepping something. So again, you would have a closed circle at 2, and then you would have an open circle at 3, and your step would go from 2 to 3. So this is actually going to continue all the way to infinity, because this just keeps going. We can't really draw that many steps. So I'll do one more. We're going from 3 to 4. And I'm actually going to do dot, 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 so that we know our steps will keep going. Because trust me, you don't want to draw all those steps. No, there's too many, right? Now, obviously, the same pattern happens on the negative side. So we're now going from -1 to 0, which means we are including -1. But since we already included 0 here, we don't include the 0 here. And that's going to be my steps going down. So from -1 to 0, we were at -1. From -2 to -1, we were at -2, so that's going to be my step right here. And then basically the same thing. And then dot, dot, dot to show it keeps going in other direction also. It's pretty neat because, you know, it just keeps kind of going in that sense, but yeah, it's going to be that step kind of thing. Now, you really, really want to think about this. What is our domain and range? We're going to wait, okay, because I know you know this answer. Let's start with domain. Think about what happens if I collapse this whole graph. There'll be no dots there. Okay, you got to explain that a little bit.
Oh, I think.
You can, well, because when they like
Let him finish talking, then I'll ask you.
when they like not like cancel each other out, but like all the open circles become like now that
Yes, I think you're on the right track.
like it wouldn't have one because there would.
But what would happen? I mean, you wouldn't have yet, you wouldn't have those circles left anymore, but what would happen?
They'd be on top of each other.
They would be on top of each other.
So it would be positive infinity to positive infinity? Oh, just kidding.
Think, you're right there.
No. I also.
Okay.
Oh.
Because they do overlap.
Yeah, so think about if, there used to be this little game, and you know, this was when I was a little itty kid, but you literally had to take like these sticks, which literally look like this, a little peg on one end and then an open circle, and you could connect them to make different, like maybe my generation of Legos, I don't know, Legos were there when I was a kid, but you could literally do these little shapes by just putting these sticks. One end was a peg, the other was a hole, so you could even connect them. And that's what's gonna happen, because as I collapse this closed circle is gonna fall right on top of this open circle. Yeah? Think about I'm compressing my graph. This closed circle is gonna fall on top of that open circle. So what's gonna happen is if I were to collapse this, I would actually end up getting a straight line through and through, right? Which basically means I am using all x values on my graph. Even though I am not using one here, I end up using one here. I'm not using two here, but I'm using two here. So that's what that closed and open circle is telling me. I'm not using 0 here, but I did use my 0 over here, because even though it wasn't included on this interval, I did include my 0 on that other interval. So you're actually not skipping any x value. So your domain is actually going from, yeah, negative infinity to positive infinity. But you know, obviously we're not collapsing the graph, we're just talking in terms of figuring out what our domain is. Your graph will stay as it is with the little steps in it. Now, again, take your time. What should the range for this function be? Shush. She's ready to jump out of her seat.
Negative infinity to positive.
No, that would be so awesome if it was. It's not.
I don't know.
Think.
Okay.
Because we're still keeping steps, right? We're not really collapsing. The collapsing is just for us to imagine what the domain would look like. You still have these steps. Are you using all y values? No. What are you using?
Are you just using the whole numbers?
Okay, let's build up on that. Because I'm using more than whole numbers.
So
Because these guys are not whole numbers here. If you don't answer, your ex is going to literally jump up from her seat and answer. Well, but I want to see what you guys are thinking, because I know she knows the answer. Yes. Integers. Yes, thank you so much. You are using integers. Because you're using whole numbers, but you're also using their negative counterparts, right? And you've got a 0 somewhere in there. So you are using integers only, because literally between -1 and 0, I'm not using anything in between those numbers. Between 1 and 2, I'm using 1 and 2 here, but I am not using anything in the middle of that. So your range is going to be set of integers.
So in equations where they actually give you like more to work with, you guys would write in the integers that it is.
Like, are you talking how you would write
Was it
it?
continuous forever, like was it connected for that time that you write the integers on the graph?
Are you talking in terms of when you are writing the
Like
range
it's
or
when
the actual graph?
Like when we do this with, and it's not just a parent function, or whatever, do we write all the integers that it is on the range, or how would we write the range?
So normally we write them as interval notation, right? But that's not the case with this. There's really not a way to write this as interval notation. Now, if you wanted to write it as a set, then you kind of have to fall back on the dot, dot, dots. So for the range, you could do -3, -2, -1, 0, 1, 2, 3, and then dot, dot, dot.
So when you do it, like when we do the actual one, because I know on the test it's not gonna be that. That's what we would write is just like,
I'm actually not sure what my MATLAB does for this, if it gives you options to choose from. Do you remember, Alexi, what my MATLAB does for the range for this one? It's been a while since I looked at this problem in my MATLAB. Some textbooks, and again, textbooks like to change this on you. Some textbooks actually also use it's sort of like a double stick I for the set of integers. On paper, I would accept pretty much anything. My MATLAB, no, don't remember? No?
I think it's very picky.
Okay, I will take a look at it. What I would like you guys to do is work on the next one. It is a variation of this problem where we're just changing it from x to x plus 1. See what you can do, and in the meantime, I will check my MATLAB. So here you will have going from 0 to 1, you're actually going to be at 1 now. So you're going to be one step higher. Right? So again, since all of these steps went up by 1, again, just showing you with the comparison with our previous graph, between 0 and 1, we were right at 0, but this step went up by 1, right? Which means all of these guys are going to go up by 1. All of these steps are going up by 1. So just like our y values went up by 1, same thing happens with the graph. So we've got 0 to 1, 1 to 2, 2 to 3, and again, this will keep going as we move forward. And then on the negative side, now, between -1 and 0, we're at 0. So just to show you as comparison, -1 to 0 was right here, but this got bumped up, which means he is the line that's going to be on the x-axis itself. So including -1, not including 0. And of course, it's going to keep going in that other direction. So did our domain and range change from the fact that since we raised everything up by one step? No? No, because like I said, if you still think about compressing this, we're still using all x values. So even though everything got bumped up by 1, we're still going to use every single x value in this function. And did your range change? No, because we bumped up by 1, but we're still using. Now, if we had just bumped up by half, that would be different, right? Because now we would be in between, but we bumped up by an integer, by a number 1, which means we're still maintaining the same range. So again, you can say set of integers. You can use a little symbol, whatever you want to use.
Wait, what's that little symbol for?
Integers, it's an I
Oh.
with 2
And how would,
states.
you said it'd be different if you just bumped up by a half, right? How would you write that for the range?
Well, that would be very interesting. I have no idea how to write that. I would probably write a sentence.
Okay.
It's gonna be halfway between
Oh.
integers because there's really no set to define it, right? Because you don't really have a set that defines half of the number. I think that's why we never mess around with numbers with half because we don't know how to write it. Amy?
I've seen graphs that look like this where like the little steps are vertical. Is that like in this example, this be like y plus like where the
Yeah, so your greatest integer symbol would have to be on the y, but the problem with that is they're not technically functions, right? Because if these are vertical, that means they're failing the vertical line test. But I wonder what kind of, well, not functions, but what kind of equations they are, because technically you cannot use the greatest integer symbol on those, because that's for defined as a function, right? And if these are vertical lines, then they wouldn't be functions. Do you remember where you had seen that?
No, I.
Like a math class?
I think so, but
Okay.
I don't remember.
If you do come across it, show me. I would be interested in seeing what or how they're defining it. Because I have actually not seen that. So I'd be curious to see what they do. Alrighty. So that brings us to our last part with this section. Here we're talking about how to identify if our function is increasing, if the function is decreasing, or the function is staying constant. So of course, we're talking in terms of, you can think in terms of slope. When you have a positive slope, it's always increasing. When you have a negative slope, it's decreasing. And then of course, if you have a horizontal line, basically, that's when we call it a constant. Now, the way they are defining this is we're basically saying if you're going from, well, they're talking in terms of interval, but as you're going from left to right on your graph, the idea is if your y values are getting larger, then your function is increasing. Again, if you're going from left to right and your y values start getting smaller, your function is decreasing. And then of course, if the y values stay the same, they're going to be constant. We say it's a constant function. You can see the definition here is basically using that same concept. So as we go from left to right, we're saying if the y value at a, when x is a, or f of a is going to be less than f of b, when the value of a on your x-axis is going to be less than the value of b, we're saying our function is increasing, because that means as I'm going from left to right, f of a is going to be the smaller number, f of b is going to be the larger number, right? So we're increasing. If the first number is greater than the second number, that means my function is going down. We are decreasing, and of course, if they stay the same, we're traveling horizontally. So what will these graphs look like? 3 of x, negative 3 of x, and just 3. All right, how do we graph the first one, 3 of x? Some of you should know this, even if all of you don't. How do we graph y equals 3x? Amy?
So you do like, at least this is how I think about it.
Okay.
So you go 1 to the right, like starting at the origin, go 1 to the right and 3 up, because your slope is, if you think about rise over run, it's 3 over 1. So you do 1 to the right and then 3 up.
Yeah, so think of that in the y equals mx plus b form, right? Equation of a line, which instead of being mx plus b, these equations are basically given to you in the form of y equals mx. So there's no plus or minus here, right? Which means our y-intercept is going to be at the origin at 0, 0. And then like Amy said, think about this as being slope, rise over run, which means you're going up 3 and right 1. So start at 0, 0 at the origin, go up 3, right 1, go up 3, right 1, or you can actually also go down 3 and left 1, go down 3 and left 1, which my points are a little off. So it should be a line that looks something like this, right? This is obviously a line as I'm going from left to right, which means as I travel along the line, my y values are getting larger, don't they? I'm starting at the negative side, as I'm going to the right, my values are getting bigger. So this will be an increasing function. Now I'm showing this to you in 3 different examples, but obviously this can happen on the same example also. So this guy is negative 3, which means you are going down and right to graph the same logic. Start at 0, 0, because there's still no plus or minus on that, which means our y-intercept is going to be at 0. And then going down 3, right 1, going down 3, right 1, or you can go up and left, up and left. And this graph would end up looking like something like this. So again, as I travel along the line, I'm going from left to right, but you can see your y values now start getting smaller. So this happens when we have a decreasing function. Okay. Now, how do you graph f of x equals 3? Yeah, it is going to be a horizontal line because this is actually in the form of y equals b, so it's positive 3, which means we're going to be going horizontally. So of course, as I go from left to right, my y value is staying the same. So this is a constant function. Okay. Now, just to show you the idea of if we were trying to do this on the same graph, you could have a graph that looks something like this. So if we're sticking with straight lines, you could have something that goes down, goes like this, and I don't know, keeps going. So you can have the same graph because this guy would obviously be a piecewise function, right? There's no other function that would give you all of these. You can actually also have these with curved lines. So we could have a function that's going down this way, ends up going this way, and then, I don't know, ends up going the other way. I mean, you can use your imagination, right? There's a lot of different functions, and you're actually going to have questions like this in your homework where they're going to ask you what kind of increasing, decreasing it's going to be. Now, a lot of times we define these on intervals. So a lot of times we can say like here, let's say this number here was, I don't know, -3. This number corresponding with this guy was -2. This one was 1. And this one was 2. So if I had to define on what interval my function was increasing, decreasing, or staying constant, then this side is of course going to -infinity. And right up until that I hit -2, my graph continues to go down. So I would say from -infinity to -2, which is what this point would be, my graph is decreasing on this interval. As I go from -2 to +1, so from -2 to +1, my function is staying constant, right? And then this is again in line with 1, so I would say from 1 to 2, my function is increasing. And then from 2 to infinity, what is it doing? It's staying constant. So in this one, let's say we're changing points here. So this one, I guess, is -2. This one is +1. We'll call that guy +2. So this portion is obviously decreasing, right? Because it's going down. So what would that interval be? And of course, we're imagining that these guys keep growing in these directions. So what is this interval where our function is decreasing? So -infinity to -2. Now this portion, what is it doing? Decreasing. So you are actually decreasing. Yeah, you're decreasing till 1. So even though it's changing directions, it's still decreasing, right? Okay, what's happening from here to here? Okay, and what would that interval be? 1 to 2. And on that last part. yeah, it's increasing on 2 to infinity. Now, you might have a little bit of trouble with MyMathLab, because intervals, when you're talking about increasing and decreasing, we always use parentheses. MyMathLab, for some reason, likes to put brackets. Whoever did the programming did not do a good job. So if they don't accept parentheses, change those to brackets. Just like you said, MATLAB does what it wants to do. Sometimes it doesn't listen to us. All right, guys? So that would be the end of 2.2. We've got 2.3, 2.4, 2.5. I'm hoping to finish them next week so that the following Monday we can do a test. Whatever that date will be.